Welcome to the course on digital electronics. And here in this subject, we are going to learn about electronics and the circuits used in the digital systems. Nowadays, using digital systems is very popular compared to the analog systems because of various benefits of digital systems, and that gives the importance for the subject called digital electronics. And here in this subject, we are going to learn from basics and will finally understand about the various important digital circuit building blocks by the end of the completion of this subject. So, in the first unit, we will be starting with the very basics of the digital electronics, and in the first place, we are going to learn about the number systems. What is the purpose of number system? So, number system is required to quantify anything or to measure anything in terms of numbers. So, we know that we have a very basic number system that we know already is the decimal number system. So, it is very popular among humans and it is used to quantify a large number of things in a daily life. And we know the decimal number system very well, but we'll understand the characteristics of number system, any number system, by closely observing the already known decimal number system. So, we'll go to see the various characteristics, though we know very well known the decimal system. So, we will recap the important characteristics of decimal system, which can be the understanding of which can be used to understand the other number systems that are used in digital system. So here we go first on the digital system, decimal number system. So decimal number system, as you know, it is composed of 10 digits starting from 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So basically this system originated as the human has 10 fingers for 2 hands. So counting the numbers by using fingers is the origination for the decimal system. So here you can see, as the decimal system contains 10 distinct digits, 10 symbols by which we can quantify anything, it is called as a base 10 system. So here one terminology is used repeatedly commonly for all the number system, that is called as a base. So base actually identifies the number of distinct digits that makes up a number system. And here for a decimal system we have 10 such symbols or 10 such digits from 0 to 9. So it is called as a base 10 system. And one more important characteristic is that the decimal system is a positional value system. So the meaning is, when you write a number, the number may contain any number of digits, and every digit is placed in a different position from right to left or left to right. And here the value the number has can be decided by the positional value of every digit, and each digit positional value depends on its position in the number. whether it is present to the extremely right or whether it is present to the extremely left or whether it is present anywhere between extreme right and left. The particular position at which the digit is present gives its positional value. So for example, consider a decimal number, the usual number that we count. Okay, so 5638. So normally we will write, since we are discussing now a different varieties of number systems, so we have to give certain notation for each and every number so that we can easily identify to which number system it belongs to. So here I say that the decimal number is 568. So I can represent this as shown in the PowerPoint. It is 568 included within the parenthesis with a subscript of 10. So this is the representation given to any number system, and here the subscript 10 indicates the number 568 is a decimal number. Then we'll interpret what is the value or what is the meaning of 568. So here from its positional value concept point of view. So here you can see that the digit 5 actually represents 500 because of its position, and 6 represents 6 tens because of its position in tens place, we say, and 8 represents 8 units simply. So by combinedly I can say that 500 plus 6 tens plus 8. Totally 568 gives the value for the number 568. Here I can say that 5 carries, here in the number 568, 5 carries the most weight or value of all the digits, out of all the digits. So it is referred to as most significant digit. And similarly, 8 carries the least value, least position value of all the digits that are present. That is, out of 568, 8 carries the least position value. So it is referred to as the least significant digit, LSD. Okay, so summarizing this slide, you can say that the decimal number system is a base 10 system. Meaning of which is it has 10 distinct digits to form any number, and the decimal system is a positional value system where the value of each digit depends on its position. And here we have an example of number 568, and the example shows what is the positional value of 5 and 6 and 8, and how we can combine these positional values to get the value of the number 568. And it also defines the most significant digit and least significant digit of a number. So most significant digit of a number is the digit which carries the highest positional value, and LSD, least significant digit, is the digit which carries least positional value out of all the digits of a number. So next we'll consider one more decimal number. Now this time it is 23.45. That means here we have taken a decimal number which contains the fractional part also. So here you can see, when you interpret this number, here the digit 2 actually represents 2 tens and 3 represents 3 units simply, and after the decimal point we have a digit 4. So now this 4 represents 4 tenths that is say 4 by 10, and the digit 5 represents 5 hundredths, that is it is equal to 5 by 100. So now we can, if you want to find out the value of this decimal number, you can see that it is 2 tens, so that is 20, 3 units, so it is equal to 3, and 4 tenths, so it is equal to 0.4, 0.4, and 5 hundredths, so it is equal to 0.05, and when you add up, you will get it as a 23.45. So this is the value of the number 23.45 decimal. So then how we actually got the value of any decimal number? Here you can see we can generalize. So any number is simply the sum of the products of each digit value and its position value, right? So here you can see in the very small illustration here the number is written as 2745.214 in the illustration, and here you can see that the dot is called as the decimal point, since we are now dealing with the decimal system, and the number is a decimal number, so the point is called as a decimal point, and 4 is called as least significant digit, the rightmost digit. 4 is the least significant digit, and 2 is the most significant digit. Why it is 2 is MST and 4 is LST? So that we know by the definition, that if you can see above, the position values are given for each position of the number. There you can see to the left of the decimal point, the digit 5 position, the first position to the left of decimal point has the position value 10 power 0, and the next position to the left has the position value 10 power 1, and the next position to the left has position value of 10 power 2, and the next position to the left has position value of 10 power 3, and so on. So that means in a decimal number, to the left of decimal points, the positional values will be 10 power 0, 10 power 1, 10 power 2, 10 power 3, and so on as we move towards left side. And when we move towards the right side of decimal point, the positional values will be 10 power minus 1, 10 power minus 2, and 10 power minus 3, and so on as we move to the right. So any number, any decimal number value can be obtained by taking the product of the positional value and the corresponding digit present in that position, and later adding all these or summing all these products will give you the value for the decimal number. And you can see that in the given example, the 4 position, that is to the extreme left, has a position value 10 power minus 3. So this is the least position value, position with the least position value. So it is called as least significant digit. And if you can observe that extreme left, you can see the number 2 position, and this is the position with a position value of 10 power 3. So the number 2 is called most significant digit. So summarizing this slide, you can see that we have shown how to find the value of a decimal number with a fractional value and by multiplying its position value with the corresponding digit and summing up all the products. So in the coming slide, we are going to see how we are actually counting in decimal number system. So we know actually, and we do not care, or we do not keep concern actually when we are counting in decimal, because that is the routine thing that we do. So, but here we will observe how the counting is done in precise, so that this can be applied to the new number system that we are going to learn. So here you can see diagram, it is shown that you can see, if you can see that these are the usual numbers that we will write and count. So there is nothing new here to observe, but there are few points that we need to observe. First, we need to remember that the number of digits that are present in this particular decimal system that are available to form any number or for counting are 0 to 9. Only 10 numbers, as it is a base 10 systems. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are the first 10 counts that we can make with the 10 digits of this number system. So after 10, after 9, after ninth count, we are writing the next count as 10, that means 1 0. So how we have written the next count as 1 0? So this requires one careful observation, that you can see that by writing the count from 0 to 9, we have exhausted our digits. The 10 digits are exhausted, and we have to take a new position to form a number. So in the next position, we'll write the digit 1. So in the next higher position, we'll write the digit 1, and in the units position, we'll start with 0 again. So we'll form the next count as 1 0. And after 1 0, you will get the next count as 1 1. So here you can observe that the unit position changes upward with each step in the count, right? So 1 0, 1 1, 1 2, 1 3, 1 4 up to 1 9. And after 1 9, we have reached the maximum digit in one's position. So you have to change, or you have to change the bit digit in the next higher position. So 1 should be replaced with 2. So with 2 in the higher position and in the units position, you can again start with 0. So the count goes as 2 0 2 1 2 2 up to 2 9. And now units position has reached the highest digit. And now you can see in the tens position, we have to change 2 to the next higher digit. It is 3. So it is 3 0 up to 3 9, and so on up to 9 9. So with one digit, you can count from 0 to 9, and by using two digits in a decimal system, you can count from 00 to 99. And when you reach 99, what is the next count? In the units position, we have reached highest digit 9, so the next digit must be 0. In the tens position also, you have reached the highest digit 9, so the next digit must be 0. So then we have to write the one digit in the hundreds position. So here you can observe one thing, that the units position changes upward with each one step in the count, and the tens position changes upward for every 10 steps in the count. That means you can see tens position, for example 1 0, the 1 changes to its higher bit after 10 counts, that is from 1 0 to 1 9, 10 counts are completed. So 1 changes to its higher bit, higher digit 2. And similarly from 2 0 to 2 9, 10 steps are completed in the count. So 2 must be changed to its higher digit 3. Similarly 30 to 39 and 40 to 49 and so on. Similarly the 100th position changes upward every 100 steps in the count. That means starting from 100 to 199, we have finished 100 steps in the count. The 100th position changes upward, that is to 2 after 199. So it becomes 200. And we can see that using 2 digits here, a summary, using 1 digit in the decimal system, we can count 10 different numbers, that is starting from 0 to 9. And we can say that I can count from 0 to 10 power 1 minus 1. 10 power 1 is 10, 10 power 1 is 10 minus 1 is 9. So that means 0 to 9 I can count. And by using 2 digits, we can count 100 different numbers, that is from 0 to 99. So this I can write in a different way, 0 to 10 power 2 minus 1. Using 2 digits, so 10 power 2 is 100, minus 1 is 99. Similarly, using 3 digits, I can count 1000 different numbers from 0 to 999. So that means 0 to 10 power 3 minus 1, whereas 10 power 3 is 1000, minus 1 is 999. So if I use 3 digits and 3 positions, then I can make 1000 counts from 0 to 999. So this is all about the decimal system. Though we know it already and will be using it every day, there are few important characteristics. So we will be repeating those important characteristics again. We will summarize the decimal number system. The decimal number system, as the name implies, it contains only 10 digits, and only these 10 digits should be used to form any number or to quantify any information by that number. So since we have 10 digits, distinct digits, this decimal system is called base 10 system. And the decimal system is also called as a positional value system, because each and every position of a decimal number will have its positional value, which is a power of 10. And the positional values, if you can see, to the left of the decimal point, the position values for the various positions will be 10 power 0, 10 power 1, 10 power 2, 10 power 3, and so on as we move to the left from the decimal point. and the position values will be 10 power minus 1, 10 power minus 2, and 10 power minus 3 as we move towards right, away towards right from the decimal point. And these position values are uh, mentioned as the powers of 10 because the base of the decimal system is 10. And to get the value of any decimal number, we have to multiply the positional value of each position with its corresponding number, corresponding digit, and finally sum up all the products. Then you will get the value of the decimal system. And this is how the decimal number gets the value. And after that, we will have seen the decimal counting, how the counting actually happens in decimal system, and how we'll be using the same 10 digits to form the next higher count. So first 10 counts will be the first 10 digits starting from 0 to 9, and the next 100 counts, and next 100 counts we can see they are formed by using 00 to 99, and 1000 counts we can count the numbers from 0000 to 999. So this is how the counts are formed, and the same concepts will be used to understand the other number systems which will be used in digital systems. So though decimal system is used by humans or in everyday life, it is the least used system for the digital systems, because all digital systems basically uses the electrical voltages to represent digits. So in decimal system we have 10 digits. So for an electrical system or electronic system to represent 10 different, to produce 10 different voltage levels for 10 different digits is very difficult. So most of the digital systems will use a lesser number of number systems with, or work on number systems with less number of digits. So what are those number systems that the digital systems are going to use frequently, that we are going to see in the next slide? So the number system which is mostly used by the digital systems is the one called binary system. What is binary system? So binary actually represents, gives the meaning of 2. So as the name implies, the binary system has only 2 symbols or 2 digits. And these binary digits, in short, they are called as the bits. And what are the 2 digits that the binary system uses? Since there are only 2 starting from 0, it is 0 and 1. So 0, 1, 0 and 1 are the only 2 symbols or digits used by your binary system. So normally we will call it as 0 bit, 1 bit. So only 2 bits are used by your binary system, and with these 2 bits only will form any number that quantifies a particular thing, right? So since the binary system uses only 2 digits, it's called as a base 2 system. And this binary system, like the decimal number system, is also a positional value system wherein each binary digit has its own value, own positional value, expressed as the power of 2. So if we compare this with the binary system, decimal system, there you can see the positional values are powers of 10 because the base of decimal system is 10. And here for binary system, the positional values are powers of 2. That is, if you can see the small diagram is there, and you can see that there is a point, the number 1011.101. Okay, and this is a binary number, and you can see that the number contains only digits 0 and 1. You cannot use 2, 3, 4, 5, etc. because it's a binary number from binary system. It can use only 1 and 0 to form any number. And here you can see it is 1011.101. And here you can see that this dot is normally called as a binary point. So since this is a number from binary system, this is called as a binary point. And you can see how the position values will be given for a binary number. You can see the position values to the left of binary point. You can see for the first position it is 2 power 0, and for the second position it is 2 power 1, and for the next position it is 2 power 2, and for the next position it is 2 power 3, and so on. Okay, so the positional values for a binary number system will be given as 2 power 0, 2 power 1, 2 power 2, 2 power 3 to the left of binary point as we move away. And the positional values will be 2 power minus 1, 2 power minus 2, 2 power minus 3, and so on as we move to the right away from the binary point. So overall I can say that the binary number system is also a positional value system where each and every position has a positional value which is expressed as a power of 2. Right, so next we will consider one particular binary number, and we'll see how it can be expressed or how we'll get the value of that binary number. So here we can see the number, for example, taken for example is 1011.101. Here I cannot call it as a 1011.101 because the position value of the leftmost one is not 1000 here because it is not taken from, it doesn't belongs to decimal number system. So binary number should always be read as ones and zeros. So the number I have to read it as 1011.101. So since it's a binary number, I can represent it in a particular notation as 1011.101 within parentheses followed by a subscript 2. So this notation tells that the number within the parentheses is a binary number. And next we'll see the same number. You can see that how to find the value of this binary number actually, or how it gets the value. So the value of this binary number or any number can be calculated in a similar way as that of as we have calculated the value of a decimal number. Only thing is the position values will be different. For a decimal number system, the position values will be powers of 10, and here in the binary system, the position value for the number will be powers of 10. Okay, so to find the value of the binary number, the given binary number, what you have to do is multiply each digit with its corresponding positional value, and here it will be power of 2. And after that, add all the products, and that will give you the value of the binary number. Here you will take an example of 1011.101, a binary number, and here you can see here the leftmost one forms the most significant binary digit because it will have the highest position value. So from the diagram you can see that how the position values are given for this particular number 1011.101. So to the left of the binary point, the first digit 1 has to power 0 and the next one has to power 1. The next digit 0 has to power 2 and the next bit has to power 3. And to the left of to the right of binary point, the first digit 1 has a position value of 2 power minus 1 and next digit 0 has a position value of 2 power minus 2. The next digit has a position value of 2 power minus 3. And here if you can see the rightmost digit 1 has the least position value of 2 power minus 3, so it is called as least significant binary digit or least significant bit, so LSB. And similarly the leftmost bit 1 has the position value 2 power 3, which is highest among all the position values. So the one is called to the leftmost is called as most significant bit, right? So here below we have calculated the value of the binary number system by multiplying like a digit with its corresponding position value. So 1 multiplied with 2 power 3, the MSB bit, followed by 0 multiplied by 2 power 2, followed by 1 multiplied by 2 power 1, after that 1 multiplied by 2 power 0. So these are the bits towards the left side of binary point. Now come to the bits on right side of the binary point. It is 1 multiplied by 2 power minus 1 and 0 multiplied by 2 power minus 2 and 1 multiplied by 2 power minus 3. And when we do the calculation, we'll get 8 plus 0 plus 2 plus 1 plus 0.5 plus 0.125. Okay, when we sum up this, we'll get the total value of the actual binary number. It is 11.625, and this also becomes the decimal equivalent of the binary number. So the value is actually will get it as a decimal number, so we can call it as 11.625. So the value of the binary number 1011.101 is 11.625, and can also say that the 11.625 is the decimal equivalent of the binary number. So summarizing this about the binary system that we have learned just now. So what it tells that the first thing is how many distinct digits it has. Only two, that is 0 and 1. And in short, these binary digits are called as bits. And since the system has only two different distinct digits, so it is called as a base 2 system. So by this, the position values uh, of this binary system will be powers of 2. and the position values will be starting from 2 power 0 to 2 power 1, 2 power 2, 2 power 3, and so on as we move towards left away from the binary point. And the position values will be 2 power minus 1, 2 power minus 2, 2 power minus 3, and so on as we move towards right away from the binary point. So the value of the binary number or its decimal equivalent can be obtained by multiplying the digits of the number, binary number, with its corresponding position value, and adding all these products will give you the value of the binary number or its decimal equivalent number. So coming to the next slide, we'll see how counting happens, or we'll see how counting can be done by using binary numbers. So far we have done counting all the time by using decimal numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on up to some thousands and lakhs and crores. But how counting of the information or a particular quantity can be done when we want to use only binary numbers? So normally when we deal with the binary numbers, we will be restricted to specific bits based on the circuitry is to represent these numbers. So that means when we want to write the first two digits of the binary number system are only 0 and 1, but we may have to use 4 bits in a particular circuit because of the circuitry that is there inside the digital system. So in that case, instead of writing as a 0, simply we have to write it as 0, 0, 0, 0. So though it has same meaning, but we have to represent it with the number of bits as specified by the circuitry. So here we assume that our circuitry requires to specify 4 bits, and here you can see in the diagram that we have used 4 zeros to show the digit and the first count 0. So normally how we did the counting in decimal number system, so we have started with 0, and the first 10 counts will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So for 10 we have done 10 counts with the digits only because the decimal system has 10 digits. But what about binary number system? Here we have only 2 digits, 0 and 1. So that means we will get the first 2 counts, 0 and 1. So what will be the third count? Or what will be the next count? So what will be the next count? So here we will compare with this decimal counting. Since the decimal system contains 10 digits, the first 10 counts will be 0 to 9. And after that, how we got 1, 0. So since we have exhausted reached the highest digit 9, the next count requires 2 digits. So in the higher position we have written 1, and keeping 1 in the higher position, we have started writing the digits 0 to 9 in the lowest position. So this will give us the remaining the next 10 counts. Next 10 counts. So next position, in the higher position we have put a 1, and in the lowest position we have incremented the digits from 0 to 9, by that we got 10 more counts. And after 1 9, the units position again reached the highest digit. So we change 1 to 2. So there is a upward change from 1 to 2. And with the 2 in the highest position, in the lowest position we continued with 10, 0 to 9 to get 10 more counts, and so on. Now you can see how we will get the counts when you want to count in binary. So you can see, observe the table, the first counts will be 0 and 1. So though the counts are 0 and 1, since our binary circuit requires to specify the count in 4 bits, we have written 4 zeros for 0, and for 1 we have written 3 zeros followed by 1. Okay, so leave that. And after that you can see, since 0 1 1 in the first position we have reached the highest digit. So what we'll do, we'll update the next higher position to 1. So the next count becomes 1 followed by 0. So here, with 1 in the next higher position, we can make one more count, it is 1 1. And after 1 1 you can see the least position has reached the, both positions have reached the highest digit. So what you have to do, you have to write the count, new count, by writing 1 in the third position, right? So here I can say that the units position, you can observe that entire thing, the count, and you can observe that the units position changes with each count, and the 2's position changes for every 2 counts, and 4's position changes for every 4 counts, and so on. You can see that using one binary digit, you can form 2 different numbers, 0 and 1. With the 2 bits, we can form 4 different numbers, and with 3 bits, we can form 8 different numbers, starting from 0 0 0 to 1 1 1. And with 4 bits, we can form 16 different numbers as shown in the diagram. It is from 0 0 0 0 to 1 1 1 1. And you can see from the table and observe the counts. You can see the first position has a position value of 240, and next position has the position value of 241, and next position has a position value of 242, and next position has a position value of 243. And you can see that the LSB position, the bits will alternate 0 and 1, 0 and 1. So the units position or LSB changes with each count. And if you observe the 2's position, the second bit position, 2's position changes for every 2 counts. For the first 2 counts it remains at 0, next 2 counts it remains at 1, and for the next it remains at 0, and the next 2 counts it remains at 1, and so on. And similarly, the 4th position, you can see that it remains it's 0 for first 4 counts, and next it changes to 1 for next 4 counts, again it changes to 0 for next 4 counts, and so on. Similarly, the bit in 8 position will remain at 0 for first 8 counts, and it changes to 1 for remaining 8 counts, and next it changes to 0 for the next 8 counts, and so on. And similarly, these are the first 16 counts that we can form right in binary number system, which are equivalent to the first 16 counts in decimal number system, which is 0 to 15. 0 to 15 decimal number system is equivalent to the binary numbers starting from 0000 to 1111. And this is how we can write the count in binary number, or we can form the count in binary number. So in the next lecture, we'll see the two more different number systems. Thank you.